Dimensioning according to related parts. Parts that must fit into an assembly, dimensioned and toleranced with consideration of function and way the parts fit together. So over here on the left, we've got a latching solenoid and a latching bracket and a solenoid plunger that goes into a slide that goes on our rail. General arrangement of dimensions. Avoid crossing extension and dimension lines when possible. Stagger your dimension values. So the dimension values on a single annotation plane must not overlap in the model. And staggering clearly shows values when using multiple rows of dimensions. Now, if you have to dimension a hidden feature, dimensions may be applied to internal features in a model, and save section view to enable dimensioning where the feature isn't visible. Half section views are to show dimensions extending to a hidden portion, so you can see part of it, but not all of it. So, and avoid this when at all possible if you can. Try to have your dimensions go to visible features. Double dimensioning. The feature size or tolerance can be determined in more than one way. This is not permitted. So in this case, we've got an overall controlling dimension of 2 inches and a quarter, or 2 inches, 250 thousandths. And then we have 3 dimensions that add up to that. This isn't allowed, so one of those dimensions has to go. Otherwise, you don't leave tolerance for interpretation. So typically you would delete the 2 inch 250, or you could make that a reference dimension, and then that, or one of the 750 thousandths dimensions would have to go. Okay, reference dimensions. They may be applied to features controlled by buttons. Does not indicate an accuracy requirement, and is not considered double dimensioning. So in this case, this would be correct. You're just giving them a reference that those features are approximately the same size, but the tolerance is radiating from the corner A, and any variation in the tolerance will be seen in F, corner F. Okay, indicating a dimension origin may be required when parts must be measured from a specific point. They're used when measured value may change if the origin of the measurement changes, and needed only if the feature is not tolerance relative to a datum reference plane. So if you have a datum reference plane, you don't need that origin symbol. I've very rarely seen this symbol used. Dimension showing only one point of application. So practical for features on extremely large parts. 2 acceptable methods of this application. You can terminate arrowhead on one side, or on one end, a dimension value, no dimension line past the dimension value, and a notation indicating that the feature from which the dimension is applicable. So it's, your part's bigger than the actual sheet size. Or you can terminate the arrow on one end of a dimension value, a notation indicating the feature from which the dimension is applicable, and a short dimension line past the dimension value with a double arrowhead. Okay, dimensioning an auxiliary view. An auxiliary view is one that's not going to be your standard orthographic views. It's projected at an odd angle, not 90 degrees from each other. Shows the true shapes of a feature on an inclined or oblique surface, and the dimensions should be parallel to the specified distances. So over on the left, you see an auxiliary view of the whole pattern in the face of this angled part. and the dimensions are in line with that view. Dimensioning a section view. Section lines create need for special consideration when dimensioning. Drawn with the same thin line type as in extension lines. And break-in sections, lining permitted but not required near the end of an extension line to avoid confusion. Dimensioning pictorial drawings. So dimensions on 2D drawing plane despite 3 drawing view axes. Used alone or in combination with orthographic views, and axiometric, oblique, and perspective views can be included in this type of dimensioning. Notes used in dimensioning. Information that cannot be clearly shown through a model, geometry, views, dimensions, or symbologies. So there are specific notes, a leader with a note shown locally, or a leader with only a note number. So we sometimes call that a flag note. Then there's general notes that apply to the entire drawing. They're usually numbered and somewhere on the drawing in a standard location, and they're typically numbered or lettered in order. Separate notes and parts lists. Separate notes and parts lists tend to be in very complex products, aircraft, that kind of thing, vehicles. But separate notes lists, you might have a bunch of numbers or symbols on the drawing, and then it refers to a separate document for what those notes are. Okay, it could be a file or document separated from the model drawing containing notes referenced in the product definition. So the product definition has to call out where that note document is. And separate parts lists are really common for large assemblies. They would not always on the drawing itself as a bill of materials. It could be a file or document separate from the model or drawing containing parts in an assembly or material for a detailed part. And a note indicating the existence of this separate list must be on your data and visible when open on the model above the title block or drawing. Okay, notes on drawing sheets and abbreviations. Right or left margin of the first sheet, common location for notes list. So if you have a multi-sheet drawing, it's common to have all the notes on the very first sheet. Doesn't mean it necessarily applies to the first sheet. It could be several sheets in. Should be headed by the word notes and numbered consecutively. Abbreviations for common terms to reduce space. Standard abbreviations are defined in ASME Y14.38. And acronyms may also be used. Clearance and interference fits. Clearance fits are when internal part is smaller than the mating external part. In this application, examples could be a shaft smaller than a hole, a rail smaller than a slot, and it's typically used for moving parts. An interference fit is the opposite, when an internal part is larger than the mating external part. So an example, that's a shaft larger than a hole, a rail larger than a slot, and only use the amount required for their design function. So this is when you want your parts to be permanently attached to each other. You would use an interference fit. Transition fit permits variations that result in either interface or clearance between mating parts. An interface when a largest permissible shaft mates with the smallest permissible hole, and clearance when smallest permissible shaft mates with the largest permissible hole. Line fit is a condition that may occur based on specific tolerances. It's not a class of fit, but zero allowance between mating parts. Difference between maximum shaft and minimum hole equals 0 would be an example of a line fit or line-to-line fit. We have our basic dimension. So it's a theoretically exact dimension value applied to the size or location of a feature. It's identified by a rectangle around the value or a general note that says everything on the drawing are basic. Feature control frames. It specifies geometric tolerances that apply to specific features. And they always contain geometric characteristic symbol and a tolerance value. So in this example, the geometric tolerance symbol is position, and its tolerance is to be within a diameter of 0.011 or 11 thousandths. They're giving maximum material condition to the hole itself, and then we have a call to datums A, B, and C. Material conditions you can have regardless of feature size or RFS when no modifier is shown. Maximum material condition for a tolerance that must be met when the most material exists on the part. And least material condition for the tolerances that must be met when there's the least amount of material existing in the part. Material boundaries. Regardless of material boundaries or RMB when no modifier is shown. So the material condition applies to the actual feature. The material boundary applies to the datums, which are typically the exterior of a part. The modifier indicates applicable material boundary datum, feature is established, and maximum material boundary, and then there's the least material boundary. So the title block tolerances, common past practice. It's still used, but they should not be used for location dimensions, and should be basic and geometric tolerances applied to those instead. Okay, chaining dimension is also a past practice. Application of chain dimensions in combination with plus and minus tolerances for location. They are ambiguous origin and direction of measurement when features form a orientation variation. So they're kind of falling out of fashion, and it's not a good way to control the features. Okay, baseline dimensioning, past practice. So baseline dimensions with direct applied tolerances for locations of surfaces. Ambiguous origin and direction of measurement when origin features have form or orientation variation, and improved methods of using datum features and applied application of geometric tolerances explained in the following chapters have replaced this. Baseline dimensioning's plus and minus location tolerance is also a past practice. Application of plus and minus tolerances on baseline dimensioning for location should be discontinued, and it's ambiguous and does not explain all possible variations. So we've gotten to the summary. In summary, this lesson on general dimensioning requirements provided you with the foundational skills needed to apply proper dimensioning techniques using the correct line types, letter sizes, arrowhead forms. You learn how to strategically place dimensions and tolerances on annotation planes in models, ensuring clarity and accuracy. Additionally, we explored the best practices for dimensioning to achieve the desired fit and function of the parts, as well as the preferred methods of specifying part requirements. The lesson also covered the application of general and specific notes on a drawing and introduction of of the different types of fit between mating parts. By mastering these concepts, you are equipped to create precise and professional technical drawings that meet industry standards. The objectives to review: by the end of this lesson, you were able to apply general dimensioning methods using the correct line types, sizes, and arrowhead form, understand the placement of dimensions and tolerances on an annotation planes of a model, apply dimensions using the best methods to achieve the desired fit and function, and utilize preferred dimension placement to provide clear part requirements specifications, and apply general and specific notes on a drawing. And lastly, cite the general types of fit between mating parts. Thank you for sticking with me on this lecture, and I will catch you in the next one.